Welcome to Applied Business Analytics. This video is an introduction to logistic regression. There are many types of models called regression models. We call them linear regression, logistic regression, probit regression, tobit, multinomial, ordered multinomial, Poisson. There are many regression models. All of them have a similar setup where you have a bunch of explanatory variables x and you're trying to somehow use them to explain some response variable y. In linear regression, our response variable y is continuous or nearly continuous, and we're trying to have some x's explain what's going on with y. In this set of videos, we're going to talk about how do you explain a 0, 1 y, often called a binary y. So we have a y which takes on the value 0, 1. Usually 1 is defined to be a success of some nature, a 0 is defined to be a failure of some nature, and we have a bunch of explanatory variables, some x's. Now, in regression modeling, we never make assumptions about the x's. The x's can be continuous, they can be discrete, they can be 0, 1. We don't really care what the x's are. The interpretation of how they affect the y or relate to the y differs, but we make no assumptions about the x's. However, we do have to worry about the y's. So when we do linear regression, our y's are continuous or nearly so. Logistic regression is a specific type of regression that you do when your y takes on two values, 0, 1. And we'll see in this video why we need to worry about a different type of model when our y takes on 0, 1 values. Y regression does not work as is, linear regression that is. As an example data set, we have data from what's called Lending Club. And Lending Club is a peer-to-peer lending system where people want loans and they go on and they give information about themselves and what they want the loan for. And then users of Lending Club can go in and give a little bit of money. They can diversify and give a little bit of money to different loans. And the idea is that this is a peer-to-peer lending. So it allows people that would not qualify or do not live in an area that has traditional financing to get financing for whatever project they need. So kind of a really cool idea. And of course, you want to have some idea of what loans get paid back and what loans default, don't get paid back. And that's what our data will look at. So we have data on 9,578 three-year loans that were funded through Lending Club between May 2007 and February 2010. And there's a variable of interest called default, and that indicates whether or not the loan was paid back in full. And we care about that. So if the loan's paid back in full, we'll get our money back as people that loan the money. If it's defaulted, we won't get our money back. And right now, we're just going to look at the borrower's FICO score. And that's a credit worthiness score. So everyone has a FICO score. A fantastic score would be above 800. I think the lowest is around 200. So go say 200 to 900 or so. Higher is better for FICO score. If you want to follow along what we're doing here and play along yourself, here's the data set. It's called loans.csv, and you can read it in online. And we just make it easier to use. We don't have to type in a lot of letters. So the y variable here is going to be default. And it's 1 if it was a default and 0 otherwise. So we want to model the probability of a default. We want to model y equals 1, I should say. I got a little ahead of myself there. But the interest here is modeling y equals 1. So what factors affect whether or not a loan was defaulted? So y is what we call a binary variable, a 0, 1 variable. And it takes on two values, 0 if the loan was paid back and 1 if the loan was not paid back. So we're interested in modeling what factors affect y being 1. Well, if we just look at a scatter plot here, this is a scatter plot of y versus FICO score, and you can see not that useful. You can't really say, oh, if FICO is less than 700, then definitely y is 0, and if FICO is above 700, y is 1. Separation doesn't seem to be that useful here. It's all over the place in terms of relationship between y and the FICO score. Now, what we normally would do, or what people might naively do, is you run the linear regression. If the only tool you have is a hammer, every problem looks like a nail. And so let's see how linear regression would address this problem. Let's use linear regression for the loan default problem here. Now, bottom line though is, what do we assume about the response variable in a linear regression? we actually assume it's continuous, and it's not continuous here. So what are we actually modeling? And let's check that out. We're fitting a regular linear regression model here. Nothing fancy, using our LM stands for linear model. So we want to model default as a function of FICO. And here's the summary. And it looks like we need FICO in the model, all that stuff. Here's the regression output again. We just cut and paste it so you can see it. Some observations. Okay, that's a really small p-value. There is a linear relationship between FICO score and default. So you need FICO in the model, we would say. How do we interpret this? That's scientific notation. It's this number. It's a negative number there, so that's why we say decrease. How do you interpret that? Well, the usual interpretation of regression is as x goes up by 1 unit, y is affected by b1. So b1's the relationship. B1 is the slope here. That's the relationship between FICO and y. So as FICO increases by 1 point, so 1 unit change in FICO score, FICO increases by 1 point, the average response variable decreases by 0.001445. That is saying that as x goes up by 1 unit, on average, y is affected by b1. So in this case, as x goes up by 1 unit, your FICO score goes up by 1 unit, y goes down by minus 0.001445. How do we interpret that in the case that y only takes on 0 or 1 values? Does that actually even make sense? Well, here's what we call the fitted line plot. So this is what we might call y hat, or we might call that the fitted line plot. This is our plot of fitted values. It's sort of weird looking because our y's can only take on 0 1s. Our model doesn't know that. These are our predicted y's, and they take on all sorts of values there. It's a linear, it's a line with a negative slope because the coefficient was negative. But this is what happens when you run regression on 0 1 data. The regression model doesn't know it should only be predicting zeros or ones. It's going to predict what it's going to predict. It's going to give you a line, but the actual data is 0 1. So there's sort of a dichotomy there. It's sort of a clash of ideas where we're giving you all kinds of values, and we should only be giving you values of 0 or values of 1. What are we actually modeling here? Well, this is what the linear regression model says. It says y is a beta 0 plus beta 1x plus noise. So it says that there's a true intercept, there's a true slope, there's noise in the system. You can already see that maybe regression is not the right model to use here, in that this is usually continuous. This is 0 1. So we don't have apples equal apples here. We have apples equals oranges. Where on the right-hand side, we have a continuous variable. On the left-hand side, we have a 0 1. That doesn't really make a lot of sense. It turns out what you're actually modeling is the probability y equals 1. So when you do regression, you can find out behind the scenes what you're actually modeling when you do linear regression on 0 1 data is you're modeling the probability y equals 1. All right, so we go back here. So we're modeling the probability y equals 1 in this model. So this says that as FICO goes up by 1 point, the probability y equals 1. Y equals 1 is default. So this says as FICO goes up by 1 point, the probability of default goes down by 0.001445. Okay, that's sort of a nice interpretation. As FICO goes up by 1 point, the probability of a default goes down by 0.001445. And we know the higher the FICO, the better. This says as FICO goes up, probability of default goes down. Everything's great, right? So this is what we're doing. So if it's 0 1 variable and response variable, and you run it with linear regression, you're modeling the probability of a default. Well, there's actually a little bit of a problem here. So this is what we just said. We can interpret this as saying as a 1 point increase in FICO, probability of a default goes down by 0.001445. Let's do some predictions. Just throw in the values of x's here. So FICO is 650. If you have this FICO of 650, we predict the probability of default is 0.25. How about I have a FICO of 825? That's considered a very good FICO. So if you have a FICO of 825, the probability of default is minus 0.005. It's a very rare event. That's such a rare event actually can't happen, because we know probabilities can't be negative. So there's a little bit of a problem here in that you get an interpretation that is believable. As FICO goes up, the probability of default goes down. However, you don't get valid predictions. And this is what happens when you apply linear regression to a 0 1 response variable. The signs will be okay, and you'll get an idea of how the x's relate to the y. Your predictions will not be good, because the linear regression model knows nothing about the fact that y can only take on 2 values, 0 or 1. What you actually end up modeling are probabilities. But again, the model does not know probabilities can't be negative or bigger than 1, so your predictions are going to be absolutely weird. So if you model a binary response variable using linear regression, you're modeling probability as a linear relationship with a predictor. And then the problem with that is that your predictions could be out of range. Fortunately, there's another type of regression model better suited to model probabilities called logistic regression. I'm going to give it away with the title of the video, and we'll learn more about this in the next video.